What did you say?
Anand, it sounds quite faint.
Yes, very faint.
I just got to turn on the mic. Sorry.
Really can't hear you.
Can you hear me now?
Yes,
Yeah.
that's better. That's better.
The mic
yes.
was turned on. Shane turned the mic on. Okay.
Okay. Okay.
Anyway,
Sure.
what I asked Zoe was how was her trip? That's what I asked.
It was
How
good.
the trip
It was good. In spite of the storms.
Despite storms, yeah. Okay.
Okay, so final talk today is by Anand Pillay on the canonical base property and internal fibrations. Thanks.
Okay, so I'm here in person, at least in person with myself at least, and a few people in the audience here, and I plan to use the blackboard. Is that okay with everybody?
Yep.
No,
Why?
Dave doesn't like it.
Why?
I'm using a blackboard, and okay, so thank you for the invitation to this talk, to give the talk. Am I visible to people?
Yes.
Like
Yes.
to Dougal,
It's good.
Zoe, etc., Udi? So first of all, I want to just say happy birthday to Udi. Udi's been a good friend and colleague and collaborator since we first met around the time he was a student, maybe 85, maybe in Maryland. I don't know where we actually met, but we worked together before that, but we met maybe a bit later. Anyway, so just to, I'm going to say a few words. Is that in the 80s, Udi transformed stability theory especially with his thesis and later stuff. From the 90s onwards until now, he's both transformed model theory as well as the connection of logic to mathematics. Okay, and I think Tom gave a good description of things at the beginning, and Dave will talk about Udi's work later. And I should say that I want to say that the intellectual history of this period, from I know model theory since the early 80s, late 70s. I think that history should be written down somewhere in some reasonable fashion. And in fact, I gave this course in Fields together with Itai Kaplan and Gabe, and the first few lectures were a bit devoted, if you remember, to talking about that history a little bit. And so it would be nice to systematically talk about, as part of history of mathematics, part of history of model theory, a lot of things. Anyway, good. So I'm going to start talking now. So what I'll talk about is the canonical base property. CBP stands for the CBP, canonical base property. And this originated in work with myself and Ziegler in around 20 years ago, exactly 20 years ago. Later on, Rahim was involved, Zoe was involved, made important contributions. And I will maybe focus a little bit on some recent paper with Remy Jaoui, Leo Jimenez, and myself. And this is also connected closely with a little bit also recent, but this is a preprint 2020. I think somebody out there is refereeing this paper, okay? So hurry up. Sorry for being so rude. Sorry for being so direct. But anyway, recent, Jerry, and then there's also Pallison and myself, Daniel Pallison from 2017. And also this is based on Hrushevsky, Pallison and myself, from I think it appeared 2013, appeared 2017, preprint 2020. Okay, so let me start with the introduction. I'm going to take this happened to my course. I'm taking my glasses off. I'm going to leave them here. Somebody remind me that they're there at the end, okay? Otherwise I'll leave without my glasses. So informally, what's going on? We're going to talk we are doing, this is model theory. I'm assuming a little bit of knowledge of stability, but I will try to give some definitions. So typically we work in, I just introduce the material, then talk about more recent things towards the end. The interesting thing maybe more recently is connected with examples and non-examples of various properties that I'll talk about. So informal. So we have we work in a T, finite rank theory. By this I mean a stable theory where every type has finite U rank, like a finite Morley rank theory. Okay, theory of finite Morley rank, but a stable theory or super stable theory where every type has finite dimension in the sense of rank or and informal. So CBP says informally let X, maybe I'll call it Z, ZC, say C in S, I'll say like this, be a family, a definable family of definable sets. So the notation means that C is a kind of canonical parameter for Z, living inside some ambient definable set. And fix A, let's call this, I don't know, let's call this Y for some reason. I should call it S, but let's call it Y. And let YA be the set of ZC such that A is in ZC. Just C in some place, let's just say C. Look at the collection of definable sets containing a point A generically, say generically. So we've got a family of definable sets in a given ambient definable set. Look at the ones passing through a certain element. Okay. So we have a family of sets. Look at the ones passing through this element A. Then this is the set, then YA is controlled by or controlled, or say parametrized by something like a definable algebraically closed field, by something like approximately a definable algebraically closed field. This is wrong, okay, but it's just, so it's controlled by something, in a sense I make precise, by an algebraically closed field, for example. Or an algebraic variety living inside an algebraically closed field, an ambient algebraically closed field. This is CBP. This is the CBP, okay? And it was proved in the paper with Ziegler for the finite rank part of differentially closed fields, characteristic 0. What I mean is this is an infinite rank theory, but you can fix some parameters or empty set and work with all definable sets over those parameters of finite Morley rank. That's a many sorted theory, finite rank. That's what I mean. I will say a few times the finite rank part of a theory, I mean that. Okay. In the strong sense, where the relevant differential with the algebraically closed field is the constants, is the field is C, field of constants. All right, so a moving family, if you take a moving family of definable sets, all of finite rank, the ones passing through a given point is more or less controlled by an algebraic variety living inside the constants. This was CB, so we proved it. And just to say briefly that a groupified version of this statement, of this thing, led to a rather direct account of function field Mordier-Lang in characteristic 0, as well as the dichotomy in characteristic 0, the Hilbert dichotomy in characteristic 0, avoiding risky geometry theorem and using differential jet spaces, and also very motivated by complex geometry theorems. Okay, any questions? Let's give a more technical, let's now give a technical, I'm going to go up here to technical definition, more technical definition. definition. So to smooth things out, often in, if you work in a kind of geometric context, you have like a variety or something like a differential algebraic variety, and its canonical parameter is a kind of, you work with its canonical parameter, like field definition of some variety. In the general model theory, you haven't got varieties, so we work with complete stationary types in place of varieties. Okay, so to smooth things out, we work with now, consider a stationary type. What's my notation? Stationary type, let's call it P, C. Again, in the finite range situation, stationary type, say P, let's say X, but I call it variable, but C, where C is the canonical base. C is called canonical base of P. It's a code of P. It codes up the type P. Okay. If P is a generic type of a irreducible variety, it's just the field definition of that variety. And let A realize P, C, then strong type C over A is almost internal. Zoe used this expression to the family. Is it okay writing here? Okay here? Yeah. P and M of non-locally modular types of rank U rank 1. Okay, and what is almost internal mean? So this is a stability theoretic efficient way of describing what I said here in terms of definable sets. Okay, so C over A, C is like the generic point of the family YA. That's the idea. And this is controlled by, which internal. What do I mean by that? Let's go over here, where i.e. after naming some generic parameters, let's say A containing A, C is in the definable closure or algebraic, is in the algebraic closure of the base set, let's say A, together with realizations of types in P and M with base, with domain living in A. Okay, this is algebraic. And when we say DCL, we'll say internal. Okay.
Anand, hi Anand. This is a definition of what?
Of what I said. I said almost internal, i.e., right? That is this. Okay. So definition of almost internal to a family of, was that Kobe? Was that Kobe
Yes.
there?
Yes, yes. I thought you were defining a big notion. Sorry.
Actually, IE, okay. Yeah, I'm saying, okay, I'm doing it a little bit informally, if you don't mind. I'm saying something, namely, okay?
What is this capital A supposed to be?
Some set of parameters, generic parameters. You add some more parameters. Of the additional parameters, you get control definable or algebraic over.
But C, but these parameters cannot contain C, for example.
Pardon? They're generic, sorry, I should say. C independent from A over A. Generic parameters, generic to C. Thank you very much, generic to C. Okay, little interlude.
One question. Can I ask something?
Sorry?
Yes. Are you assuming elimination of imaginaries or something like that?
No, I work in EQ.
Oh, okay.
I always work in EQ. Okay, if nobody minds. Okay, let me just say, so I'm going really unbelievably slowly. I don't know why I'm going so slowly. Let me just say that almost internality. internality to a family P of partial types over empty set gives rise to a Galois group. Let's call it Gal. Let's say P. It also depends on the base. I mean, P may be over. I mean, PX could be over a set. Could be over a set B. Okay. Internality in general. You see, the notion of internality makes sense. I said IE, but you could extrapolate to a general sense of what the meaning is for an arbitrary set P of types. Okay. Internality to family partial of, say, strong type of some type, say PX, QX, say, over B, Galois group of, say, Q over B, let's say P, which is the permutations of realizations of Q induced by automorphisms fixing B and realizations of P pointwise. Okay. Good. Okay, equals permutations of the set of realizations of Q induced by automorphisms of the ambient structure fixing B plus realizations of types in P pointwise. So in the above situation, B is my A, and B is my A, and C is my realization of the type Q. Okay. Okay. This is definition of almost internality in the canonical base property. Okay. In terms of CBP, we're going to make additional assumption. Is all non-locally modular rank 1 types are non-orthogonal to the empty set, which means there is no infinite moving family of non-modular rank 1 types, non-locally modular rank 1 types. We make this assumption. All natural examples have this property, and in DCF0, the finite rank part, the only up to non-orthogonality, the only one is the constants. Okay. In this case, let P NM non-modular int be the set of types of, say, anything D over the empty set, such that a strong type D over the empty set is internal to PNN. So we work with, and then internality to PN, internality to PNN, and to, let's call this PNN int, let's call this Q for now, are equivalent. Also, Q is internally closed. If some type over the empty set's internal to Q, it's already in Q. Okay, and so now an instance. So from of internality, even almost internality to P and M gives rise to a Galois group by replacing P and M by Q, which is over the empty set. So then you get a Galois group by what I said over here. So we get a Galois group witnessing. Now, okay, now question. And to do this, you need the assumption that that I made at the top of the board. So the motivation is, does every finite rank T, with the assumption above, let's say, have the CBP? That was a question. And Udi, over the years, I know we asked about this in early 2000s after formulating the CBP. Then Udi suggested over the years a few counterexamples. Eventually, one of them, I'm not sure, maybe Udi remembers what panned out or not, but one of them I worked on with Daniel Pallison, and it worked out. So we wrote a paper with Udi about this. That's a 2013 paper. It's a nice example. There's more recent examples by both Leo and Michael Lush, student at Amador. And so Udi also suggested, in some informally, that that rigidity of the relevant Galois groups could be of relevant Galois groups with respect to internality to something. Rigidity means no infinite definable family of connected definable subgroups. These will be finite Morley rank groups, actually. This is connected or implies the CBP. We said something in a paper in 2013. We wrote a couple of things. We made some observations. Then with Daniel Pallison, in the later paper, we worked out some more details showing that actually this rigidity of Galois groups was equivalent to a strong form of the CBP. Okay, and that's what I want to talk about. So PP. And for this, we had to work with Q rather than with P and M. Okay, so the following are equivalent. For a finite rank theory, one, whenever P, any type, type over B, is, let's say, internal to Q, where Q is precisely what I said here. It's the types over the empty set internal to the family of non-locally modular rank 1 types. Then the Galois group of P over B Q is rigid. And rigid means no infinite definable family of connected definable subgroups. Or in other words, every connected definable subgroup is defined over algebraic closure of the base set, such as abelian varieties or algebraic tori in ACF. Okay, one thing. And two, whenever C is canonical base of strong type of A over C, very special situation, then not only is the type of C over A almost internal to Q, which is the CBP, but also then C is in the algebraic closure of A together with Q. It's algebraic over A together with realizations of types which are over the empty set internal to Q, okay? So the point is, in this situation, once you pass the Q, you need no additional parameters like A before to witness the internality or the almost internality. Here's ACL. And by the way, almost internal is more or less the same thing. If some type of something is almost internal, that it'll be interdefinable into algebraic with something which actually is internal. So passing to internal is not a big deal. This was it, right? That was the statement. And we called 2 the strong CVP. So this was an exact statement which is connected with the Galois condition, okay, which Udi suggested. And the point of working with Q is that this notion is it's robust notion. It's robust, which means it doesn't depend invariant under naming parameters. Okay. I should say briefly, without writing anything down, that there was a strong connection to Leo Jimenez's thesis. He was studying internality, if you want, of functions, Q to P, and internality to some family of partial types over the empty set. And that internality of a function meant that the fiber type A over pi A, or A over FA, is internal. And the question, and Leo constructed a groupoid connected because there's a base and a groupoid, and you have a notion of collapse of the groupoid, and collapse of the groupoid exactly means that A is an algebraic closure, pi A Q. So passing from P to Q to the internal closure of P was closely connected with, and it's also robust. So, right. Any questions? Any questions? I'm going a little bit fast, but I wanted to talk about the examples. I'm sorry if it's a bit. Anyway, problems. Some problems are yeah, so notice this implies that the Galois group of the type of C over A, a Galois group of, say, what? Of the type of C over A, C, Q, is finite. That's what it means. Okay? It's already in the algebraic closure of. So, questions, examples, non-examples. Non-examples. Another thing is to even weaken strong CVP to discuss, to weaken the condition on this Galois group. Okay, so can you, are there various gradations of the canonical base property where, for example, could there be, right, I mean, in CVP, you have that strong type C over A is, let's say internal to Q. So you've got a Galois group. For example, you could ask, could there be an absolute bound in a given theory on the dimensions of those Galois groups? And the Galois group, really what it measures is how many additional parameters you need to see the internality. So it measures something. Okay, so there's weak and strong VP to say something about this. For example, is there always an absolute bound on the Galois group? Anyway, but let's say something about examples. So let's say some examples from CVP. So suppose you're in a theory, finite rank theory, where everybody realizes is in Q. And this is the analog of an almost strongly minimal theory. So let's give an example. Consider the finite rank part of pairs of ACF. This is an infinite rank theory, pairs of algebraically closed fields. If you work over the empty set, there's the only finite rank thing around, even in EQ, is actually the bottom field. After you name parameters, you get more stuff. So let's name some parameters anywhere and you get a finite rank theory. But every A, realize every A is in Q. So Q is everything, which means anything, yeah, that's it. Every element in a finite rank part is actually real, is type of the empty set is in Q, is type is internal to, in this case, the bottom field is the unique non-modular, is a unique rank 1 type. So that's one example. So strong CBP for trivial reasons. Another example, finite rank part of DCF. Of DCF 0. In the paper with Daniel Palacin, we said, yeah, this doesn't have strong CBP because of differential Galois theory. There are differential Galois groups with respect to the constants, which are not rigid, such as PSL, PSL2, SL2 of the constants. But this was a bit, but it just turned out that when talking with Remy and Leo, this didn't exactly work because we were talking about internality. So ordinary Galois theory is with respect to the constants. We're with respect to Q, which is the constants internal things to the constants. So you have to do differential Galois theory over an additional invariant set, namely things internal to the constants, and it's not, and you have to see that you still preserve these Galois groups. And this also, you can do it and it works. So it shows that. So, but it needed an additional argument because you're now doing Galois theory with respect to a larger invariant set. Okay, and we had to use the fact that any Pikov SM extension of a field of constants has commutative Galois group. Okay, we have to use that fact, which is an interesting fact. We expect this will go through for ACFA when suitably modified or generalized to work with this quantified, like what Zoe was talking about, quantified free internal. So we expect the same idea goes through. But what maybe is a bit interesting in the final few minutes is to talk about, CCM. Another example, CCM. This is the many sorted theory of compact complex manifolds with the sorts of the compact complex manifolds, and the relations are the complex analytic closed subvarieties, which are locally given by zeros of holomorphic functions of Cartesian product powers or products of sorts. This is a theory, and that theory is a very nice theory, and it's analogous to the finite rank part of DCF 0. There is one non-modular strongly minimal set, which is P1 of C, so CCM. So P1, the actual standard model, has a sort projective line over complexes, which contains all of algebraic geometry. But there are lots of other things around which are not connected with this, like generic complex tori, generic K3 surfaces. There's lots of interesting. In fact, we made some conjectures about some years ago with Rahim about the identifying trivial rank 1 types in connected with hypercalar manifolds, but we didn't look at it for a long time. Anyway, so this is and the standard model, everybody's names. M is the standard model. And there, P1, let's call P1C, I'll call it P, because you work over, in this model, every element's named, because you name all, because every point itself is a subvariety. And so P, it equals P int. So because you work over a model, Galois theory with respect to P is the same as with respect to P int, Q. And what goes on there? Well, this we studied a bit more in detail in the paper with Remy and Leo, and so where's the to actually work to do some internality, you've got to be working a non-standard model. So you have M, and you have M, right? You have M and you have M star. And you're working with types, you know, PX over SB, where B is in M star. Or it could be a 1 point, okay? B, you're looking with types like this. And non-standard model. And typically a type like this, if you have a model here and you have a top point outside B, you have this type, and you can, and B is a generic point of some family definable set here, and this P will come, and there'll be actually a fibration down here, say X to Y, in the standard model. This is the generic type of the fibration. So all these types come from things in the standard model, okay? So the key is to look at, so at some point, I think Rahim suggested to Remy, when Remy was a postdoc in Waterloo, to look at look at an example of Matteo Toma. For some reason, I don't know why, Rahim, maybe why did you ask him, Rahim? There was some question he asked you or something, an example about of certain holomorphic vector bundles. Okay, no, anyway, so we're going to find, so in fact, I can ask, I can ask generally, what is the analog of a linear differential equation in CCM? And one possible answer is it's like a generic fiber of a holomorphic vector bundle. Okay, and okay, so let's do it. So take a CCM. Let CCM. When I say a CCM, I mean Y be a complex manifold as a sort, and E is a holomorphic vector bundle over Y. So this is in the complex analytic category. So you only have really local charts. It's not like, yeah, it's not obviously definable, but PE is the projectivization we have this PE goes to Y, and this is you make every fiber, you make actually a projective space rather than a vector space, and the whole thing you make and the whole total space PE becomes a compact complex manifold, not necessarily projective, but fiber-wise projective. This lives in CCM. This is a map definable in CCM, and we want to consider, and it looks like these kind of things are in some sense analogs of linear differential equations in the context of CCM without adding a derivation. And right, then given, so let S be in Y star, which means a big model, and let P, E, what I want to say, S, what I want to say, star S is the fiber. So you have, right, you have pi star goes to the non-standard version to Y star. Okay, and we take the fiber, generic fiber, let S be in Y star, generic. So if Y is irreducible, there's a unique generic type outside, realized over the model. So and let P, E star, S be the fiber above S. Right? Then, using facts about projective bundles, which are not totally obvious at first sight by definition, it turns out that this is internal to, it's internal as a definable set. It's internal to, let's call it P or P star. P is the projective line. Let's call it P star if you want to work in the big model. And an example of Matteo Toma So Matteo Toma example, I think it's from 1989. I'm not sure. So you know, in the case of complex manifolds, lots of work goes on in the algebraic category, where you look at these objects for algebraic varieties. And I'm not sure to what extent there's really a lot of interest in non-algebraic, in the things outside, which by non-algebraic, I mean complex manifolds, which are orthogonal to the sort of P1. They exist. But anyway, so what the example was of what he calls a strongly irreducible rank 2 bundle E, holomorphic vector bundle E over Y, where Y is, say, a generic K3 surface or generic algebraic torus. Not algebraic torus, complex torus of dimension 2. So these are both generic complex torus dimension 2. So these will both be for generic they'll both be strongly minimal. It's the same way as in differentially closed fields, you have order bigger than 1 equations whose solution set is Morley rank 1. So they'll be, and strongly irreducible, it really means irreducible means there are not, so it's actually P, so over Y. So you're looking at PE so this is, E is rank 2, it means that PE, each fiber is projected one space, a copy of one's is projected one space. Strongly irreducible means, if I remember, that there are no algebraic sections. There's no multi-sections. There's no subvariety of PE, which maps onto Y, and such that the fiber above a point is finite. So there's no algebraic multi-section. And strongly means even after passing to I think finite covers or something like that. Anyway, so then the theorem, then the Galois group, then we prove the Galois group on this situation of PE star S with respect to both S and P star is just the P1 in the big model is naturally isomorphic to PGL to C. In fact, the actual argument uses orthogonality of Y to algebraic geometry.
C
In fact,
star?
yeah.
C
Question?
star?
No, actually C. It actually is, well, it depends. What we're doing is we're working in, what you do is do this. What we do is, it's very similar to differential Galois theory, actually. You take M, you take this generic point S, okay, and you work in the prime model over M together with S. So it's a little bit like working in the prime model over CT when you're doing in differentially closed fields. Look at that prime model. It's a TT theory, so the prime model. Then in fact, in this prime model, because this S, this type is orthogonal to P1, to the complex field or C star, when you take this prime model, there are no, so if you want C, the points of C in M is the same as the points of C in M. It's like no new constants. It's the analog of no new constants. So it's rather amusing. And then in fact, as in differential Galois theory, you get this fiber corresponds actually to a group living in the orthomorphism group corresponds to something living in the constants. Okay, so that's it. So we get the non-strong CCM. So we get the so CCM not strong CBP, and so I mean in this situation, so yeah, so to see the Galois theory, it helps to have orthogonality of the base. And by the way, in the case when the base Y is itself an algebraic variety, Gaga tells you that PE is itself an algebraic variety by Gaga. So everything is internal. So to get any interest in Galois theory, you have to work with the base is orthogonal. Well, the base has actually is at least not an algebraic. It doesn't live in the P1 sort. And I guess a couple of questions is maybe it would be interesting to try and look at the inverse Galois problem for holomorphic vector bundles, or these projective bundles, and what can you produce there? Anyway, so yeah, so why non-strong? Because I'm using here the Galois theoretic condition, the Galois theory criterion about rigidity. This group is not rigid. Did I say PGL2? I wrote that already. Galois group PGL2C, which is not rigid. So I'm using the Galois. I'm not working here directly with canonical bases. I'm using the Galois criterion for strong CBP. Okay, so there's two things, I guess. One is doing a kind of inverse Galois theory for holomorphic vector bundles may be interesting, but one has to work with bases which are not algebraic varieties, even over strongly minimal sets, where the bases are strongly minimal set, number one, and number two, just what is the connection with classical notions? So I guess in earlier talks by Jean-Benoit Bosch, there were talks about the H0 about sections of vector bundles or whatever, but maybe we're interested in number of algebraic sections, multi-sections is connected with this Galois. Anyway, on the face of it, naively, this is another model theoretic invariant of an object in complex geometry. What else? Do I want to say anything else? Maybe I'll say quickly that the original motivation for doing the CBP was motivated by results also in complex geometry by Campana about showing, actually, I'm going to stop. No, I don't want to say any more. So I think I'll stop here if nobody minds, and then maybe if there's questions, I can say something. Thank you.
Okay, thank you very much, Anand. Thank you. So, other questions?
Right, he has a question. Oh, so